Cool. So, then without any further ado, let's begin. So the OSI model, oh man, once upon a time there was something called the TCP/IP model. TCP/IP. This was made basically by the United States government and the Department of Defense, and it was created as a model to explain how networks operate. It was all fine and dandy, but maybe not quite complex enough to explain how they actually operate. Like it simplified some things and maybe too simplistic. So then they created this thing called the Open System Interconnect model, or now we just call the OSI model. And this is an international standard 7498. This international standard is a bit more complex than that TCP/IP model and aims to explain how networking operates, acting as sort of a framework and guideline on here's what's going on in the background, right? And all the time I see this chart sort of presented as this is the OSI model. Everything you need to know is here. But I don't feel like that's quite right. It doesn't really explain what's going on. We are going to go ahead, though, and review a couple parts of it, and then I'll show you how it works. But again, this international standard, the OSI model, is just a way to explain how networks operate. And having an understanding for this makes everything else a little easier, I'm going to be honest. So follow me through a little journey here into this OSI model. Hopefully you'll get a little bit better feeling of how messages traverse the network. At the very top of the model, we have something called application. A big mistake that I usually see is people think, oh, application, this must mean like Microsoft Word, PowerPoint, Photoshop, programs. Not quite. This layer is the layer where you find the languages, though, that those programs would use to talk across the network. So you're seeing like my web browser, let's say Firefox. My web browser will use the language HTTP to communicate with a web server. And that's the type of languages here that are part of this level, right? HTTP, the hypertext transfer protocol, it's a language of web traffic, and my web browser would use that language to send messages to a web server. Similarly, like a tool like Outlook, which would be actual software, might use the application language SMTP, the simple mail transfer protocol, to send an email. We've got FTP, file transfer protocol. We've got Telnet, remote command prompt from one computer to another. Well, the list goes on. There's thousands of these application level protocols, these languages that computers speak to communicate over a network. But all right, that's just the start. Then we have this level down here called presentation. At this level, it's all about formatting, it's all about syntax. There's a lot of compression that takes place at this level. Like if you were to send perhaps a large email over the internet, maybe there's a way to compress it, make it a little bit more efficient. That's going to happen at this point. This is where we find things like JPEG, ASCII code, the letters and numbers and symbols on your keyboard, MP3s, GIF, and so forth. Um, you know, it's a layer that involves a lot of formatting and preparing something like HTTP traffic to traverse the network. I also have this thing down here called the session layer, right? The session layer, it keeps track of all messages that are going out of your computer so that when replies come back, it can figure out which reply was tied to which request. If I send 100 messages to Google asking for 100 different pages, and then Google replies, let's say once, which reply does that tie to which reply is that to which request? This whole level takes care of that. If you ever type like netstat in your command prompt, you can see all the records of where your computer's going and where the messages are coming from. That's the session layer in a nutshell. It's tracking communications from one side to another. This is pretty important. Now, all of these top layers really happen on your CPU. Like in that chip on your motherboard, that CPU, like all of that's happening. And all of these are really tied, if I'm going to be honest, to functions of your operating system, or to the softwares, that you might have. But in the end, You know, these are important layers for creating what is just called data that we want to get across the network. Now, I want you to picture data like a letter that you want to send, like a conventional letter you're writing to someone, not that we do a lot of that anymore, but like you're written a conventional letter, you're going to put it in an envelope and put it in the mail. Well, we got to put that data in an envelope. And the next layer down addresses that. Another thing that the CPU is heavily involved in, but as we keep working our way down, we see like our network card getting and network drivers getting more and more involved in this process of basically taking data and packaging it up, taking a letter, putting it in an envelope, or what we call encapsulation. You see, we're going to take that data and we're going to put it inside of what is called probably a segment. Take that letter, put it in an envelope. Now, every good envelope should be labeled, with what is called a port number. If this is a HTTP traffic, we're going to label this thing with a port 80. If it's SMTP traffic, we're going to label it with a port 25. It's basically numbers written on the outside of the envelope, that tell you what type of traffic you're dealing with. If I see, port 20 written on the outside of the envelope, that tells me I'm dealing with FTP traffic, the file transfer protocol. Cool. Well, that's all well and good, mark this thing as fragile, perhaps, by writing that port number on there, but it doesn't tell me where I'm going. It doesn't tell me where I'm going. So our next layer will handle that. The segments are placed inside of packets, and at that point, we put an IP address on the front of it. Kind of gives you an idea of where you're coming from and where you're going to. Source IP and destination IP, just put on the front of this message. But that's not all. We've also got MAC addresses. Right? Sort of the difference here being, picture IP addresses like going from town to town, or from street to street, or from like one apartment building to the next. If I go to another town, that doesn't tell me which house to go to in that town. If I go to an apartment building and the IP address just tells me which apartment building to go to, I don't know what apartment in the building, though, I'm looking for. The real world equivalent of that, I suppose, for these addresses is the IP address helps you find a network, but the MAC address helps you find an individual node inside of that network, a singular device that's in that network. And here we have yet another address, a MAC address, that sort of gets put on the front of yet another envelope that tells us which specific device we're going to inside of that apartment building or inside of that other network, inside of the other town. And that's kind of cool. But yet more addresses being like tacked on a thing, basically envelopes being put inside of envelopes, a tremendous amount of encapsulation. Eventually, once all that is done, the message is broken down into your classic 1 and 0s, we'll call bits, and then just fired off across the network. 11010 as electrical signals or light if you're dealing with fiber optics. Right? Okay. Interesting. Let's look at it a little closer. Let's go through this, step by step, not far off from what we just did, but a little closer and actually see sort of visualize some messages being built. Right? We're going to send a web request to, let's say, Google. I want to go to www.google.com. Now, in order to go there, I got to use DNS to find out the IP address of the Google server. But once that's all handled, it's time to put our web request together. And that all happens at layer 7 of this OSI model, the application level, right? Where we find our fundamental network languages that the programs in our computer services use to communicate. So Google Chrome puts together some data, right? We'll say this specifically is HTTP data. We got HTTP, HTTPS, DNS, FTP, SMTP, POP, IMAP, SSH, Telnet, and that is a short list. I could probably put about 10,000 things on this list. Again, there are so many different languages that our computers could use potentially to speak across the network. But if I'm just going to a web server, and an HTTP sounds fine. Google Chrome or Firefox makes this message, and it's quite large. It could be streamlined. It could be better prepared for transit. Anybody who has moved from one place to another knows that you got to fit everything in the back of the truck. And There's not enough space on the internet superhighway for extra trucks. We need to try and get this in one truck. We need to get it to fit into one message, for the sake of efficiency. We need to pack it in there, Tetris things in. Our next layer down handles that. Presentation. Within your computer, the second that HTTP data is created, it starts taking the message, reformatting, compressing, making it more appropriate for transmission, adjusting as needed, right? Cool. So formatting, conversion, compression, encryption, maybe decryption. Here's a weird thing about encrypting things. That, though, can happen at just about any point within this entire model. There's about a billion places you can encrypt something, but commonly it is layer 6. But okay, we've taken our message, we've compacted it a little bit, we've prepared it to be sent a little better, and then we can move on to the next layer. Session. Your operating system says, all right, hey, hold up here. This message, I'd love to send it. This language even is traditionally sent using what is called TCP, as opposed to something called UDP. Now here's the deal. The TCP system, you ever heard the story of the tortoise and the hare? Right? You got this tortoise, very, very slow, doesn't move very fast. And you got the hare, the rabbit, who's quick. They decide they're going to have a race, right? Everybody's convinced the hare is going to win, including the hare. They're very boastful. They said, oh, there's no way a tortoise could beat me. If we are in a race, I will win every time. Except they start the race, right? Tortoise and the hare both start. On your mark, get set, go. Turtle, nice and slow. Hare does like 3/4 of the race and goes, man, I'm so far ahead, I don't even know where the turtle is. I bet I could afford a little nap before I finish this race. Goes, takes a nap. And then while they're sleeping, the turtle, slow but steady, finishes the race. The tortoise is TCP. It's slow, but it's steady. It's reliable, but it's not fast. UDP is your hare. It's fast, and it sometimes doesn't work. Bringing up a classic networking joke. I could tell you a joke about UDP, but I'm not sure you'd get it. But you would get it. It's just not reliable. It doesn't always work, but it is fast. We traditionally use this in any place where we basically want instantaneous communication. So Zoom. Right now, my voice and video is being sent to you as UDP traffic. The downside is, however, it could at some point just boop, cut out, and then, well, that's it. There's nothing to be done about it, because that's just how UDP is. Like, there's no retransmission later, no making up for the fact that the video cut out. It just did. It's gone. Move on with life. But TCP would be like, whoa, hey, video cut out. Let me resend the missing data. Let me make sure everything gets there. Everything's got to be perfect, even if that makes me incredibly slow. Well, HTTP uses this TCP pretty much, not exclusively, but pretty much all the time. Lots of TCP being used here. And if I am just going to www.google.com, that's certainly going to be the case. And the session layer knows it. And the session layer says, wait. If this is TCP, TCP is like a good house guest. They don't show up uninvited. TCP's always got to be invited. So what's going to happen is my session layer is going to hold my message up. My message is getting ready to go. It's, hold up, man. Hold up. While we call ahead, while we make a connection, wait. And once the other side says they're good and ready and that you're welcome, then we'll send you. Otherwise, hold your horses. You're staying right here. So we're going to hold our message here while TCP opens a connection, makes reservations, and calls ahead. And assuming the other side is good, then we can proceed. But also note, though, again, this layer keeps track of everything that goes out, makes records of everything that leaves. So when messages come back in, we know that message is, a reply or tied to our previous message. So TCP says we're good to go. Send it. Down to the next layer, transport. At this point, right, we're going to encapsulate. We're going to add, a header onto the front of that message. We're taking our letter. We're putting it in an envelope. We're going to put a TCP or UDP header on the front of that data. And we've already decided this one is TCP. So TCP style envelope, big sturdy envelope, kind of heavy. Again, TCP kind of slow, kind of clunky, but your message will get there safe and sound. UDP, tissue paper envelope, kind of reckless. But all right, we're going to use TCP, and within that system, they use port numbers, right? So we got to tag this thing. You might recall I said HTTP uses port 80, so that's what we're going to slap on the front of it. TCP, and it'll say on that this is port 80. You might say that doesn't sound important. Well, later, as this message goes across the internet, or crosses a network somewhere, anybody who looks at it can see that number 80 on it and go, oh, this must be web traffic. And that's kind of important, like for them to be able to identify what they're handling. If I have a letter, I might just chuck it into the back of a mail delivery truck. But if I have something that says fragile and it's full of glass, I'm hopefully not going to chuck it. Knowing what type of traffic you're dealing with is kind of important. So putting that number on there helps us identify what we're dealing with. Now we would call this complete message, because yay, terminology, this complete message would be called a segment if it is TCP. And 90% of the time, yeah, it will be, because most things are TCP based. But if you were doing like we are doing now with Zoom and you are doing real-time streaming, you might be using UDP, and then this message would be called a datagram. In fact, UDP stands for the User's Datagram Protocol. So that little D in there actually just stand for datagram. Again, though, it's not enough. We got to put IP addresses on the front of this thing to say where we're going, what network we're coming from, and what network we're going to. So let's take care of that. Next step down, slap some IP addresses on the front of it, right? That's what we're going to do. The network layer is responsible for connecting different networks or local area networks together. We're going to be using things called packets. We're going to be using routers to send these messages, but even more importantly than that, the IP addresses again. On the front of that TCP and UDP header, we're going to glue another header, basically like taking one envelope and putting it inside of another. And this packet header will contain a source IP and a destination IP address, where you're coming from, where you're going to. We'll investigate those IPs in a minute, but okay, put IP addresses on the front. Now, when this message goes across a network, a router will be looking at those IPs to decide, should I send you this way? Should I send you that way? And we're going to look at that too in a minute. All of this message is called a packet. Inside that packet, in this case, is a segment, and inside of that segment is data. Get our terminology down properly. Still, though, alas, this is not enough. We got to put MAC addresses on the front so we can say which computer we're going to in a specific network. Sort of tells you what the next hop is in your network. What is the next network device you have to reach? Or like which apartment you're looking for in the apartment building. Let's get those MAC addresses on the front of it. The next layer down, data link handles that, right? We're connecting two nodes together inside of a network. We're creating now what is called a frame. This whole thing is called a frame. And inside of that frame, specifically on its frame header, are these MAC addresses. There'll be a source MAC and a destination MAC, again, where you're coming from and where you're going to. But that specifically tells you like where you're at right now and what's the next immediate device you're going to. And those go on the front. Now, switches, bridges, and wireless access points will be entirely deciding, you go this way or that way, based off of the MAC addresses, which is, again, kind of different from routers, because routers are looking at IPs. But all right. Now you've got this fancy looking frame here, including this thing at the end, this frame check sequence, or FCS trailer, they call it, just there to detect electrical interference. Now we've got this frame and it's ready to transit. It's ready to go. So we send it over the physical layer, the very bottom layer of the OSI model, where the message is just going out as bits, ones and zeros. Beep, 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 beep. Ones is on, zero is off, and we transmit over the physical equipment. Right? All the electrical signals and how they work, or optical signals, or magnetic waves in wireless, are all managed as part of this level. And out they go as bits. Now as we work down through these layers, last time we're going to use this vocab word, we encapsulated. We took one message and put it inside of another. That's pretty important. But you know what's cool? When my message makes it to Google, we're actually going to end up going in the other direction. Remember, that's the whole premise of this. I was sending to Google, right? I put my port number on here, of 80. I put my IP addresses on here of my computer and Google's computer. I put the proper MAC addresses on the message as well. And then we sent it out at ones and zeros. When we get to Google, though, it kind of all backwards. They're going to receive the message as a bunch of ones and zeros, as a bunch of bits. And once all those ones and zeros are all lined up in a row, they've got their frame. And then you know what they're going to do? They're going to look at the MAC addresses on the frame and say, are these correct? If they are correct, and this message is meant for me, good. If not, bad. And if bad, we drop the traffic, we delete it. Assuming that this message is indeed correctly addressed, it comes into the Google server and it's got the right destination MAC address for Google on it, they're going to be happy with that. They're going to check this little trailer at the end, make sure there was no electrical interference, which is basically like if you took the whole message and added it up into a number, say 102. If I re-add the whole message up, it better come out to 102 again. But assuming everything looks good there too, they'll be quite pleased. And you know what they're going to do at that point? They're going to delete the MAC addresses. They're going to delete that little trailer. They're going to take our frame and they're going to de-encapsulate it, basically strip off all that stuff, and we're back to being just a packet. But then Google's going to check the IP. Is the IP addresses correct? As in, did you send to the right destination? If you didn't, if this mail isn't for me, I'm not going to open it and I delete it. But if it is meant for me, if Google's IP address is the destination that they see there, great. In which case they then delete the IP addresses and we're left with just the segment. They look at the port numbers. Do we have any software on the Google server that answers to or uses port 80? Oh, we do. The Apache software here uses port 80. That's the web server software. Great. In that case, send it to the web server, and they then delete the port numbers. And you're back just to being data. Now, if this message says it's part 1 of 2, they'll make sure they get both parts, 1 and 2, here at the session layer. Once they got both the parts, they'll hand it to the presentation layer to properly glue them back together, decompress as needed. And then the software will then be given some data here all the way at the top, layer 7, to just read. But you end up like de-encapsulating, taking things out of envelopes as you work your way up through the layers. I think that's kind of cool. So this is a deep dive into our OSI model, and then it helps explain a lot how networks operate. Now, what we're going to do now, unless there are any questions, is take a look a little bit at the MAC addresses and the switches that sort of govern layer 2.
You provide great explanations.
Thank you. I'm glad. That is my job after all. Glad to hear that. So that MAC address, that pesky MAC address, actually stands for Media Access Control Address, because like anything else, acronyms in IT, right? Acronyms galore. MAC is Media Access Control Address. Well, we just call them MAC addresses today. Part of layer 2 of the OSI model, or the data link layer. Side note, knowing what the names of the layers are is somewhat helpful. Not a bad thing, especially if somebody says to you, oh, there's a problem with data link. You immediately know like where to look and what type of devices, are having problems. Good for communication. Now, these MAC addresses can also be called physical addresses or burned in addresses or even Ethernet hardware addresses. Because why not have a billion names for the same thing? It really just comes down to the fact that these MAC addresses are built into every network interface card that exists. In order to access the network, you have to have a network interface card. Um, that might be built into your motherboard. It might be a separate expansion card, but one way or another, there is a network interface card for every computer so that they can plug into the network or have Wi-Fi. There's always a NIC. And when these NICs are made at the factory, they are given a MAC address burned into them. Well, it's kind of burned in like you brand cattle in a sense. They set the MAC address using software, and then they actually send too much electricity into it to basically make it so the MAC address is burned in, melted in place, set inside of that chip permanently for the rest of its life. They're basically branded. So at that point, hey, MAC addresses could be called burned in addresses because they're burned into the network interface card. And they physically, are, if you got like an electron microscope out, you could, and shaved off some part of the chip, like you could potentially visualize and see what it is in a sense. So it's kind of physical. It physically follows that card around. It's tied to that physical card. Now, these MAC addresses are 48-bit long addresses, which means 48 ones and zeros. But reading 48 ones and zeros, 110101110, would be obnoxious. So what we do is we view them instead as 12 hexadecimal characters, where each hexadecimal character is 4 bits. So for example, if we look all the way up top, this hex character number 1 is actually a 4-bit value. I know what that one would look like. It would look like 0001. And the letter E is also a 4-bit value. This guy, let me think, what does it look like? 1110. They're all 4-bit values, and there's 12 of them. 12 hex characters. Let's see here. 12 times 4, because each one's 4 bits. Well, that's 48. And here you have a 48-bit address, where the hex characters can be anything from 0 to 9, or A through F, where A is like effectively 10, B is 11, and so forth. And you get an address that looks like this. That's a MAC address. Now, interestingly enough, right, when these MAC addresses are assigned to the cards at the factory, the first half of the address is called an OUI, Organizational Unique Identifier. It basically tells you who made the card. So if I look at this MAC address, these first 6 hex characters are my OUI. They're the vendor. Tells you who made it. And you can actually look these up on the internet. Say MAC address, 1E D4C9, and go, made by Dell, made by Intel, made by Cisco. That's kind of cool. So who made it is actually the first half of the MAC address. Now let's say this company here, we'll say Matco, 1 Echo Delta 4 Charlie 9. That's the MAC address OUI we've been given, and all of our cards will use that. Now, the very first card my factory makes will probably be 00:00:00. The second card will be 01. The next card will be 02. The next card will be 03, and so forth. And every time we make a card, we just sort of increase that last little part, which is specific to the network cards that we are making. Eventually, we'll get to 97 Charlie Bravo 61, as seen here, But all in all, still, you can always look up the first half of the MAC address and know who made it, which is kind of neat. Now, these MAC addresses, right, which we're going to find here in every single message going across our network for the most part, right, is important to our switches. Because when traffic comes into a switch, they're going to be looking at that MAC address to decide, which of these other ports should I send the message out of? Like if a message came in, say message came in here, should the message go out any of the other ports? Should it go out that port? Should it go out this port? Should it go out that port? Which port should we go out? It's, an important part of this. So switches forward traffic based off of the source MAC address found in any frame. Realize my image is a little too big. I can cut off part of the letter F there. Found in any frame, right? All right. So let's look at a switch here. This is the international sort of network diagram icon for a switch, like basically a box with 2 arrows to the left and 2 to the right. There's our switch. We're going to imagine the switch has got port 1 and 2 and 3 and 4, several ports, and connected to it several computers, A, B, C, and D. Now, I want to keep things nice and simple, so we'll say this computer up here, computer A, is the MAC address of A. This guy down here is the MAC address of B. This one right next to me is the MAC address of C. Yes, MAC addresses are longer than that, but, we make things easy here where we can. Inside this switch is something called a MAC address table, sometimes called a CAM table, which is just MAC backwards. The MAC table, the CAM table, this thing keeps track of which computers are connected where. So computer A is connected to port number 1, and you can see that in its table. Interface number 1 connected to MAC address A. Interface number 2 is connected to B, interface 3 is connected to C, interface 4 is connected to D. This is important because let's imagine a little message is coming down this wire on the left-hand side, and if you were to look in the frame header, it says source MAC equals A, destination MAC equals D. This message comes into the switch, and the switch says, which way should I send it? Should I send it to port 2? Should I send it to port 4? Should I send it to port 3? Which way should it go? Oh, it's not too tricky, right? You can simply look at the table. Look at the table, right? If you're trying to go to Delta, your destination MAC address is D, you should go out interface 4. And that's exactly what the switch is going to do. It's going to send out interface 4. Doesn't need to send out 2. It doesn't need to send out 3. Just out 4. The end. And then out it goes. So again, it looks at the MAC address to decide where to forward traffic. I think is neat. If it isn't sure, for example, your alpha was trying to send to a destination of echo, and that's not in the table, it will hedge its bets by sending to every port. We call this flooding the message because it doesn't know where the destination is, so it sends to everybody. But otherwise, so long as it knows, it will send specifically to whatever port in question. You try to go to destination Charlie. According to our table, that is interface 3, and down it goes. Any questions there? Does that make sense? Now, one of the cool things about switches is VLANs. And this is where you really get into I'd call the real heart of a CCNA course, configuring devices. It's a big part of the test. It's at least 3 questions on the test where you actually get a command prompt and have to configure something. And I'm going to kind of give you a little look at how to do that now, specifically for these fancy devices. And we're just going to imagine we're setting up VLANs. Now, what is a VLAN? Well, at the moment, assume all the devices you see here, A, B, C, D, are all part of what we'll call VLAN number 1. And if that is the case, they're all in the same VLAN, so we could assume they can all talk to each other. VLAN stands for Virtual Local Area Network. They're all in the same local network. They're all in one, so they can all talk. But what if I broke that up? What if we go into this switch and we set these 2 ports here, 1 and 4, to be assigned not to VLAN 1, but let's say to VLAN number 2. And then we select the 2 bottom ports, 2 and 3, and we assign them to be, let's say, VLAN 3. Well, now we've done something very interesting indeed. For all intents and purposes now, this switch behaves like 2 separate switches. You have A and D at the top, ports 1 and 4, both assigned to VLAN 2, so they can talk to each other. Traffic can flow from A into the switch, across, and then back up the delta. Because basically, for all intents and purposes, same VLAN, the switch will let them communicate. One of the reasons for that, we cover in a CCNA class, is that ultimately speaking, alpha and delta would both be in the same MAC table together. So that means A can talk to D and D can talk to A, and that'd be fine. It'll allow that. But you wouldn't be able to talk to B and C. Alpha and delta, A and D, cannot talk to B and C. Bravo and Charlie down here cannot communicate with them because they're in a different VLAN. Right? B and C can talk to each other, but they wouldn't be able to talk to A and D. And one of the reasons for that is they would have their own separate MAC table that put them together in their own table, meaning they can send to each other but not to anyone else. So by simply reconfiguring these ports, logging into the switch, typing in some settings, you've made it so A and D can talk, B and C can talk, but not to each other. You've taken one network and virtually split it into two different networks as if you had two different switches, albeit we only have one, which I think is pretty cool. Now to configure this, there's some steps. Sort of as a golden rule, if you're going to be using VLANs, you've got to give them a name and pick a number. Kind of important. Give them a name, so you remember what they are. So what I've got here is a virtual machine switch. This is switch number 1. Well, imagine the switch in our diagram, right? And I want to configure those ports to be assigned to different VLANs, and I need to make the VLANs and name them first and foremost. To sort of get into what we call privileged exec mode, admin mode, where you have the ability to change things, I need to type in enable. And we then see the symbol there change to a pound symbol, meaning I'm logged in, I'm in. I'm going to type in configure terminal. This gets me sort of into my editing mode we call the global config. Now comes the fun part. VLAN 2. We're going to say VLAN 2. I don't know. Computers A and D, the top two computers. We'll call that VLAN number 2. Although I do need to put the word name in there. There we go. VLAN 2, name computers AD. Right? And I don't even need to exit this. You can see it put me into what we call a subconfig. I'm now able to control VLAN 2. I don't need to do anything with that. I've already given it a name. I'm going to just hop right over to VLAN number 3. And we're going to give that guy a name. Computers Bravo Charlie. Enter. Interestingly enough, in the Cisco operating system, it's only at this point when I've left this configuration, the configuration for VLAN 2, that it actually enables it and gives it a name. Weird quirk, which means that VLAN 3 doesn't exist because I am currently editing VLAN 3, having just given it a name, and until I exit this config, it will not exist. It's kind of weird. But it's one of those quirky things you learn to live with here. Notice that once I exited the config, boop, now it makes VLAN 3. So now we've got VLAN 2 created. We've got VLAN 3 created. We got to assign them the ports. Now this is a virtual machine running a pretty high-end switch, all things considered. So it's not just ports 1, 2, 3, and 4. They've got more grandiose names. You can see several of the names sort of referenced up top. To get a sort of a list of all the names of all the ports that exist here, I'm using abbreviations. The command is show IP interface brief. Well, let's see here. We have a fast Ethernet 01. We have fast Ethernet 02, fast Ethernet 03. We got a fast Ethernet 8, a gigabit Ethernet 01, a whole bunch of different ports here. So in this case, this virtual machine doesn't even have anybody connected at the moment to 3 and 4. But we can imagine for the sake of this that maybe they do, and still show how to assign these VLANs to those ports. Of course, if you've done it once, you've basically done it 100 times because it's kind of the same commands over and over again. Right? I'm going to type in config T to get into my global config, my editing mode. more abbreviations. There's a lot of abbreviations allowed in this system. I'm going to type in fast. Let's see our interface F01. Specifically trying to get to this guy. Enter. And now I can say switch port mode access, switch port VLAN, switch port access, VLAN 2. So what has this done? This first command told them that this now is going to be assigned to one VLAN as opposed to not many. The switch ports are allowed to be part of one VLAN or all VLANs, and they can kind of change their states. We're setting the state, we're setting the mode of this port. So it's just going to be one VLAN. And what VLAN is that? VLAN number 2. So that port's now set, right? Let's say this port here, fast Ethernet 02. Now that needs to be part of VLAN 3. All right. Interface F02. Enter. I use my arrow keys to bring up my old commands. Bring up switch port mode access. Enter it again. Bring up the old command for VLAN 2, but change that to be VLAN 3. Hit enter. And there, once again, I've configured some VLANs. So now, fast Ethernet 01 is tied to VLAN 2. Fast Ethernet 02 is tied to VLAN 3. If I wanted to confirm that, there's some fancy commands you can just show, like show VLAN. Some of the commands are very intuitive and very straightforward. Enter. And there you go. VLAN number 2, known as computers AD, is connected to F01. VLAN number 3, computers BC, is connected to F02. Sort of there you have it. So it's pretty cool configuring, VLANs on a switch. Not too hard to do, but certainly something that warrants a bit of practice and be a big part of a class to practice that. You get good at it. Any questions before I talk about IP addresses for about the next 15 minutes?
Nope, it's clear.
So IP addresses, on the other hand, not layer 2, layer 3, right? They're found in a different spot in the messages going across the network, or what we call the packet header. Sort of a quick rewind here. We're now looking at the addresses that are stored here instead, right? Now, if we're using old IPv4, we got 32-bit long addresses, and they look like that, right? Number, period, number, period, number, period, number. That's 32 ones and zeros, sort of broken up into groups of 8, or what we call octet number 1, octet 2, octet 3, octet 4. Byte 1, byte 2, byte 3, byte 4. And we convey them basically as numbers, where any one of these numbers could be anything from 0 all the way up to 255. But this 32-bit addressing system for IPv4, it's kind of messed up. I'll tell you why. With 30, if a bit can only be on or off, there's only 2 combinations then for any given bit, and you are going to have 32 of them. That's 2 to the 32nd power as far as combinations go. That means as far as combinations are considered, there's only 4 billion possible combinations. But that's not enough for every computer and every place on the planet to have an IP address. I mean, that's probably not even enough for the United States by itself. It's not enough IPs to go around. In fact, we ran out of all the IPv4 public addresses, the ones that were available to the public, in 2011. To solve that problem, another system was created called IPv6. The IPv6 addresses, like the fancy one I got like kind of drawn up top, right, are 128 bits long. Now this actually gives you a lot more than 4 billion combinations. It gives you 340 undecillion combinations. That's 340 trillion, 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 trillion combinations. Put that into perspective, you could give an IPv6 address to every grain of sand on the planet and every person. Still have plenty left over, which is a silly amount. But an amount we certainly won't be running out of anytime soon. Now, No matter which one you use, IPv4 or IPv6, right? IPv4 written out as those four sort of numbers between 0 to 255, number, 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 or IPv6 written out in hexadecimal and quite long by comparison. Kind of almost looks like a MAC address in a way. No matter which one you use, though, these IP addresses are actually considered logical as opposed to physical because they aren't built into the network card. They have to be configured. These addresses could be assigned statically by a person or dynamically via DHCP. In other words, you can set them yourself one at a time. That sounds like a lot of work. Or you can have a DHCP server, the Dynamic Host Configuration Protocol server, hand addresses out for you. To each your own. But every device in the end will need to have an IP address in order to operate. And remember, they're not built in. You ever want to see what your IP address is in Windows, ipconfig/all is probably a good way to go. You can actually see I've done this on my computer, albeit I've masked a couple things that might be sensitive. When we run this command ipconfig all in Windows, we can see a physical address. What is that? My computer's MAC address. If we type in, or rather we don't even type in, we just look further down, we can see the IPv4 address that my computer is currently using. 192.168.1.2. But how did it get that? How did it get this IP? We can see the MAC address. We can now see the IP address. How did it get the IP? Well, DHCP, I'm sure of it. Why? Excuse me. It says DHCP is enabled for starters. Yes, it is enabled. But also, furthermore, it tells you when we got it and how long we get to keep it, which is what makes us a dynamic, or DHCP, a dynamic system. This address was given on Wednesday at this time and is going to be allowed to be kept until Saturday at this time. So start date, end date, and my computer can always ask for that date to sort of Saturday to be extended. As long as my computer's on, it might ask to push that sort of end date back a little bit, which is honestly what's been going on for days now. I turned this computer, my server here, on Wednesday. I haven't turned it off since. And my server only usually gives us addresses for 24 hours, but because my computer's still on, it says, well, give me a little more, give me a little more, sort of meaning that I get to keep this address as long as both myself and the server are cool with it. It's a dynamic system. If I turn my computer off, though, and my computer's not on tomorrow, I'm sure this address will be released and then available to someone else on the network. But interesting. And as we said, routers forward traffic based off of the IP addresses found. Well, that's not quite right. Based off of destination IP. There we go. That's what I get for making this slide sort of a little hastily. Forward traffic based off of the IP found in a packet. So maybe we imagine a network that looks a little like this, and there you see the icon for a router, noticing how it's very different from the icon for a switch, which was a box with two arrows in each direction. Here we got a cylinder with arrows on top. Cylinder. Sometimes people just draw them as a circle with an X on top if they're being real lazy. But this router will be looking at the destination IP address in all packets. And the router doesn't have a MAC table, it has a routing table. It might look like a little bit like the one I got here. So if traffic comes up this wire and it says source IP 192.168, we'll say 1.1. That's part of this network, part of the finance network. It's one of those computers, maybe this guy. And it is trying to go to, we'll say, this ops network above me, destination IP 192.168.2. Let's say 2. We'll say that's this guy over here. This message comes into the router and it says, let me check my table. Look at that table here. It says, all right, if you're trying to go to 192.168.2.0/24, which basically means anything that matches the first three numbers in the IP address, you're good. And we do 192.168.2. We match that. It says you should go there through interface number 3. So it will. It'll send through interface 3, getting us into that other network. We change the destination, we might end up going somewhere else. What if we make the destination 8888? That's a Google server. It checks the table. Well, you can't be sending to 192.168.10/24. None of the numbers there are even remotely similar. This route I've underlined is a range of addresses, and 8888 is certainly not in it. So it's not going to send that way. But also it wouldn't make sense to, because 192.168.10 is where the traffic is coming in, not where it's going to go out. I mean, why would traffic need to come into port number 2 and go back out port number 2? Doesn't make any sense. So they wouldn't even check that. They would ignore this path. They would look at the other route that goes to interface 3 and say, you're not trying to go to the 192.168.2 network or anyone who's part of that network. Yeah, ignore that one too. At which point the system hopefully has what's called a default route. A default route means if all else fails, go this way. If nothing else works, this is the way to go. And it's usually written as 0000/0, and then tells you where to go. And in this case, it says interface number 1. So it doesn't know where 888 is. It doesn't match either of the other entries. So it takes the default path and forwards out to the internet. And that's where you'd find 8888, which is a public IP address that's part of the internet. And the router has made the right decision, sends it out in the right direction. But like, routers are all about IPs. Switches are all about MACs. And I think that's pretty cool. Very important, though, to have these routing tables so the router knows what to do with your traffic based off of those destination IP addresses. Notably, if a router doesn't know what to do, I suggested that earlier with a switch. Switch doesn't know what to do. What does it do? It sends to everybody. Routers don't handle that way. They go, I don't know what to do. I'll delete it. So it's very important to have this default path that says, when in doubt, go this way. Because otherwise, if that wasn't in the table, we didn't have that little path programmed into the table, the router would delete your traffic instead. So I don't know what to do with it. Delete it. Get rid of it. It's like, And that means then people got to be programming in default routes, or telling them what to do when it's otherwise unsure. It's another thing, like learn how to do in a CCNA class. Last thing, though, on the docket for today is a little bit of DHCP. I was thinking I could show you how to configure a DHCP server, another classic sort of CCNA topic. We note that the DHCP server is just a device that hands out IP addresses to hosts. It hands out an IP address, tells them what subnet mask they should have, what default gateway they should be using, as in tell the computers where they should send to if they need to reach the internet, and maybe even tell them what DNS server to use, like where to look up names and find IPs. There's a whole lot of things, though, that have to go into making sure a DHCP server is secure and can't be manipulated by a bad guy. But that's not something we need to immediately get into, because there are attacks against DHCP servers. But now, let's not worry about that right now. Let's figure out how to set one up. One thing at a time. Now, all of the Cisco devices that run the iOS operating system, that's not lowercase I, by the way, that'd be iPhones, but like capital iOS, this operating system is the lifeblood of Cisco. All Cisco devices that use it can be DHCP servers, even a switch. You really only need usually one on your network, though. And the server function is built into the operating system, again, sort of enabled by default. Now, when this thing hands out addresses, it will give addresses out for 24 hours by default, which is just sort of common for anything that's Linux related, like the iOS operating system. And you can also tell it addresses you don't want it to hand out, should there be any. We call those exclusions. As in this instance, what I'm doing is I'm setting up a server, sort of like a waiter at a restaurant. And I'm telling the waiter, you can't give out either of these addresses. They both need to be excluded. Do not give these out. In the first one, I'm telling them don't hand out this address. Do not give any computers the address 192.168.1.1. In part because maybe somebody's already using that. Alternatively, right, IP DHCP excluded address. This is a range. Don't give out anything from 250 to 254. Don't hand them out. We're all out of cheeseburgers. Don't offer anybody a cheeseburger. Do not offer anyone these addresses. They are off the menu. They are excluded. And if you are going to exclude any addresses, you don't have to, but if you are going to, always do that first. And you would do so by literally typing in the commands you see here. IP DHCP excluded address. Cool. You might say, why would somebody do that? Maybe these are already being used somewhere and were configured statically? Could be. Could be. There could be other reasons too, but that's probably the main one. After you've done that, you get into the real heart of it. You're going to have to make what's called a pool of addresses. The command is IP DHCP pool, followed by the name of whatever pool you want to create. So give it a name. This is a name. Be descriptive. No spaces, though. If you need a space, use an underscore. Call it my pool, call it my underscore pool. I don't really care. But no spaces. That's a name. Once you've done that and you hit enter, it'll drop you into like a little subconfig window. Now comes the fun part. First, we're going to tell them what range of addresses they should be handing out, or what network they're going to be governing, what network they're in charge of. And in this case, that's 192.168.1.0 with a 255.255.255.0 mask. You might also interpret this as 192.168.1.0/24. For those who have learned their way through subnetting, you would recognize that this basically gives you a range of the first address that can be handed out as a 1, and the last address that can be given out is a 254. Noting that a 0 is not allowed to be given out to a computer, and a 255 isn't allowed to be given out either. Because 255 is what we call a broadcast address. It represents sort of, if you wanted to send a message to everybody, you send it here, and it then sends to everyone from 1 to 254. Because 255 is reserved for a broadcast function, we can't use that. And because 0 is reserved for identifying the range of the network, that can't be used either. And you really are just left with, this gives you a range of 1 to 254, where the first address it would give out would be 1, and the next one would be 2, and then 3, and the last address it could give out would be 254. Of course, I would note there are exclusions we created already. In that case, considering these exclusions, 1 can't be given out, so the first thing this thing could actually give out would be a 2. And it's not allowed to give out 250 to 254, so the last thing it could give out would be 249. Yeah, it's like, oh, that's a lot to think about that. Got to consider the exclusions and how that affects a range. But that is what I'm doing here. I am telling this router or switch, this is a range of addresses to be given out. Anybody who's given one of these addresses should use 192.168.1.1 as their default router, their default gateway. If I wanted to, oh, go ahead. Did I hear somebody there? No, I'm hearing things. I didn't even see a hot mic. I just thought I heard something. Maybe it was outside. Could be. If I wanted to change the lease time, I can do so here. This is days, hours, minutes. The default lease time thereby would again be considered lease number 1, 24 hours, 1 day. Days, hours, minutes. So there I set it as the lease should now be, addresses should be given out for 1 day, 2 hours, and 3 minutes. Really kind of unnecessary. I almost never bother to deal with that. 24 is fine unless you're like, I don't know, a convention center or something like that. If you want the computers to be part of a specific domain, you can tell them here as such. And if you want those computers to use a specific DNS server, you can tell them as such. You should use these DNS servers. But all right, let's do it. Another cool sort of activity that you would encounter in a CCNA course. So I've got a router open here. Congrats, I've loaded my lab properly. Another virtual machine. Great place to practice. First thing I need to do is type in enable so I can get into the sort of admin mode. Type in configure terminal, which you can abbreviate down to just config T if you like. And now I'm in the sort of editing mode. All right. And let's say I need to make one of those reservations, or rather exclusions. So IP DHCP excluded dash address, and we'll exclude 192.168.1.1. Why? It's already being used somewhere else. Enter. Then I make my pool, the group of addresses I want to hand out. IP DHCP pool, and we'll give it a name. Our name will just be name, I guess. And see how it like suddenly it goes from config to DHCP config? That's the subconfig I was talking about. You're now configuring a pool of addresses called name specifically. And the first step is to give it a range of addresses. And that range is going to be 192.168.1.0 with a mask of 255, 255, 255, 0. Enter. Let's give all those computers a default router. Default dash router. I always forget the dash until I look at it. Default dash router, 192.168.1.1. And I don't know if we want to give them DNS so they can look up names, maybe 8888. Enter. That's sort of the abbreviated version of what I just, showed on the screen. I can now hit end to back out of my config, type in copy, run start to basically save my work. So you're trying to save to the startup configuration? Yes. Enter. And now I've configured a DHCP server. This router will be giving out addresses in this range, actually starting with 2 because 1 is reserved. Everybody they give an address to will get an address for 1 day at minimum. They will all be using 888 as their DNS server, and they will be using 192.168.1.1 as their default router. And just like that, I've configured a server, which I think is pretty cool. All righty. Any questions? Anything anybody like to talk about networking wise? About wraps up my sort of prepared, walkthrough here today. But I got time for discussion if you have anything you'd like to talk about or questions you might have.
Question I have is normally like when I set something like this up, it's through like a router, a firewall. Is this when you're dealing directly with the server, correct?
I mean, you can set this up on a router. You can set
Okay.
this up on a switch. Any Cisco iOS device allows you to make it a server.
Okay.
So it doesn't have to be a server like a dedicated box itself.
Okay.
Common though that people do this on their default gateway. Whatever router is closest to the internet is usually where this takes place.
Okay. Because I've done the VLANs before, set them up through all the different layers within the firewall, basically.
Okay. Yep, that's doable. Depends on what hardware you're dealing with.
Right, right. This just definitely makes it make a whole lot more sense though, watching this way.
Oh, right on. I'm glad.
All right, thank you for that. Appreciate it.
You're quite welcome.
Yeah, do you do webinars just through the training camp, or we can sign up to your webinars through other sources?
I only do webinars through training camp as I am a training camp instructor.
Okay, gotcha.
Yeah.
Yeah, this was so like very good.
I'm glad. Yeah, not a lot that I feel like I can do in about an hour, but
But your explanations are really good. Like I have never heard anybody explain ISO model and UDP versus TCP the way you did. Like I'm audit manager and I have to train junior staff. So I'm gonna steal some of your examples
Oh,
to
sure.
make it like understandable for people that are brand new to cybersec world. So yeah, it was good. How do we get CPU certificates?
I believe that's sent out automatically from our help desk team.
Okay.
Yeah, I would say give them a few days because I think they're all traveling right now to different locations for various things. But they'll probably get into that next week. If not, let me write out their contact information.
Awesome.
Yep, they handle all of those.
All right. Thank you so much.
You're
Have a
welcome.
good one. Bye bye.
Take care. Have a great day. Maybe I'll see you in class sometime.
Oh, you will. Yes, you will. Bye.
Yeah, many thanks. Have a great day.
You as well.
Take care.
If there's anything I can do for you, any questions you might have or things you'd like to discuss.